Good afternoon, my name is Mykola and I want to present to you a report on the topic Field Test Data Processing for the Implementation of Accelerated Rig Tests of Sprayer Booms. It consists from Introduction, Field Test Data Editing for Accelerated Rig Tests, Project Development and Setting, Fatigue Editing Assessment, Damage Editing, Results Assessment, Conclusion, and Acknowledgements. Field tests are an important stage in evaluating of machine's fatigue life. It gives the most accurate results, but require significant material and organizational costs to the preparation of such an experiment. In addition, a full-scale experiment requires considerable time for its preparation and implementation. The financial and time commitment for field tests can be reduced substantially using accelerated tests able to reproduce on the investigated structural the same damage produced on the machine during real life in a reduced time. With the development of controlling techniques and data acquisition and processing methods, electrohydraulic servo test rig has been widely used in the accelerated test to optimize critical performance attributes such as durability, but also noise, vibration, and harshness. An important task is the preparation of such accelerated tests in the creation of a driver file that will ensure the execution of the tests in accordance to the specified conditions and in the shortest possible time. The most effective way to create such driver files is a method which allows creating a set of data for accelerated rig tests using specialized software based on experimental data from a field test. In this study, the field test data processing are implemented using ITTAP23.Mykola software tools for the implementation accelerated rig tests of the sprayer booms. The goal of this processing is to use the field test data to prepare and drive files for a test rig. The field test data were derived from 4 channels of universal measuring system. Each of these represents an axial strain gauge placed in some potentially critical locations of the sprayer booms. The task is to edit down these channels to retain all the damage but shorten the length of the files as much as possible. This enables significant benefits in accelerating rig tests. Under test data processing conditions by specialized software tools and ITTAP23.Mykola procedure to create equivalent damage test specification for a lab, rig has been implemented according to the developed detailed design that contains the following glyphs: time series input glyph, strain life glyph, XY display glyph, damage editing glyph, graphical editor glyph, data value display glyph, time series output glyph, and frequency spectrum glyph. In the slide we can look at how damage accumulates over time. We can do this because the strain gauge data was measured against time and the fatigue damage calculations track cycles. The slide showed time histories of when damage occurred in the time domain for each channel. For the fatigue editing assessment was used damage editing glyph, data values display glyph, and XY display glyph. The next step in the fatigue editing process is to determine appropriate parameters for use in the damage editing glyph. For this, it is necessary to set the following properties of the damage editing 1 glyph: mode assessment, window minimum 0.125, window maximum 1, window step 7, percentage damage minimum 75, percentage damage maximum 100, and percentage damage steps 5. The assessment mode of damage editing glyph enables to access the effect of 2 parameters. Window length, this is the time slice of data that is considered in adjacent non-overlapped windows. In assessment mode, a range of values is defined. And percentage damage retained, given a certain window length, there will be a relationship between the amount of damage retained and the time retained. In assessment mode, the range of values is defined for the damage retained. Varying these 2 parameters was produces a family of curves: percentage damage retained against percentage time retained for each window length. The resulting curves can be used to select an appropriate trade-off between required damage retained against how much time will be saved. In this case was used a 0.25 second window length and retain 100% damage to achieve an approximately 80% reduction in time. To edit the time histories with these parameters, the process was extended so that the new damage editing to glyph creates a feature list of sections to be deleted. This feature list is then used by the graphical editor 1 glyph to perform the required edits, thus shortening the time histories. For the damage editing 2 glyph was set the following properties: mod slice selection, keep first and last true, window setting by time, window length 0.25, damage setting %, and % damage retained 100. After run the process, the slice selection mod in the damage editing 2 glyph has identified which sections can be deleted and passed this information to the graphical editor 1 glyph in the form of a feature list using a multi-column table of start and end times. The graphical editor 1 glyph shows that the sections that will be deleted, marked sections, are generally of smaller amplitude than the retained sections. In this slide, it's easy to see the effect of removing non-damaged sections in the time domain. The max and min values are the same and the cyclic content is the same, but the time duration has been drastically reduced. This will shorten the rig test time while retaining the important fatigue inputs, because these edited time histories are about 85 seconds long compared with the original 440 seconds. To examine the obtained results, it's advisable to compare them in the frequency domain. The frequency domain is another way of representing a time series. In the frequency domain representation, we're able to see behaviors that would be impossible to identify in the time domain. Time series may be represented in the frequency domain in many different formats. Among these, the power spectral destiny format is the most popular. Glyphworks frequency spectrum glyph can easily calculate the power spectral destiny from time domain data. This glyph performs frequency spectrum analysis autospectral on time series data using fast Fourier transform algorithm. Power spectrum densities of the measured and the edited signals that are compared in this slide have a good correlation. These two trends were very similar because editing doesn't introduce any anomalous peaks. And so, conclusion. The field test of the sprayer's booms can be reduced using accelerated tests, able to reproduce on the structural part of this machine the same damage produced on the sprayer's booms during real life in a reduced time. The presented procedure of the field test data digital processing by Incode Glyphworks software tools made it possible to obtain a set of edited time histories ready for use in driving the test rig. Reduced the test duration by more than 5 times, about 85 seconds versus the original 440 seconds, at the same damage level of structural, will have a huge impact on the time required to run the entire durability test in the lab. Furthermore, the test on the lab rig can be performed without interruption due to unfavorable weather conditions or the need for rest of the drive, unlike the field tests. The transformation of the obtained results between time and frequency domain showed that power spectrum densities of the measured and the edited signals are similar enough and correlate well. I'm very grateful to the company HBM and the team Incode for the possibility to use their software and for the information support. My special thanks to Lukasz Piniak, account manager Prensia. Thank you for attention.